Guys, in this tutorial we continue exploring collision detection and we do SAT today. So we did previously, in the previous tutorial we did bounding boxes, axis aligned bounding boxes, which are fine for most 2D games. However, when you have rotation, this is by the way the code that we left with in the last tutorial. The only thing I added was the rotation and the code that allows us to draw rotated entity on the screen. So now we create two entities and rotate the second entity by 45 degrees. And as you can see, even though we're colliding, bounding box technique doesn't really help us with rotations. So it says no collision even though we are actually colliding. And when we're not colliding, it says collision because the bounding box is axis aligned. So what we need to do is to have a technique that allows us to take rotations into account. And we can do so by applying separated axis theorem. This is a great tutorial on TUTS+, so I suggest that you read this first. It's quite long, but it is also a lot more detailed. And this video is going to be a sort of short version of it, more or less. So what the theorem states is that you're able to draw a line to separate two polygons, or two entities in our case. And if you're able to do so, then they're not colliding. And yeah, that is pretty much it. So what we're going to have is, well, first of all, we'll need some sort of class to contain our static methods for collision detection using SAT. And let's have another method called isColliding. They will use SAT technique rather than bounding boxes. And then we'll have static method here, which is going to be the actual logic. isColliding entity 1 and entity 2, and do some stuff and return some value. Let's do true for now. Return SAT isColliding this and other entity. And then we'll change that to isColliding SAT, and that should do it. Now, so the idea is to first of all compute all the axes on which we can project each of the corner points. But if you can look closely, then you'll realize that this is a rectangle, and rectangles only have two normals because of the fact that the opposite sides are parallel, so they lie on the same axis. So the only thing we need to do is essentially to compute this normal, which is going to be one axis, and then that normal, which is another axis. Similarly with this rectangle, it's going to be normal to this side and one of the other sides. Now the thing to note as well, since we have rotation, and we can use the angle of the rotation to inform us about the vector, which is essentially a vector obtained from the angle, which allows us to create normals by just knowing the rotation of an entity, which we know because of that variable. And this is the one that allows us to draw the entity rotated as well. So once we, yeah, let's do that first. We'll have a method that is called get, that returns a list of point2d. I'm going to use point2d as a vector as well, because this is how it is done in JavaFX. But if you're using something else, some different framework, then you'll have to implement your own version of vector2d. get axis given an angle, and that angle is going to be in degrees because that's how I defined rotation within the entity class. And we can use knowledge from vectors, which really comes in handy because we can easily obtain a vector from an angle. And it is going to be, well, first of all, we'll need some values here. So what you do essentially is just obtain cosine and then sine of the angle. Cosine becomes the x component, which we can do. Actually, I'll need to use cosine and sine in the future as well, so I'm just going to do this. Cosine of an angle in degrees is math cos math 2 radians, because math class deals with radians instead of degrees, so we convert them to radians first. And almost mirror method for sine as well. So it's cosine of the angle and sine of the angle. Now, we can also note that because of geometric properties of a rectangle, what you essentially have is the two sides that are parallel. They're also placed perpendicular to other two sides. So instead of computing anything else, we can easily obtain other axes or the other axis by just adding 90 degrees to the angle that we have. Which is actually an interesting insight because it saves us writing more code. So we've obtained the two axes for a particular angle. Given the angle, we can get the axes, and after that, we need to map those corner points onto those axes that we produce. So for each rectangle, we can obtain two axes, which means there will be 4 axes to check against. So we project those points onto axes, and then we check if they are overlapping. If they are, then there's a collision. If they are not, then there isn't a collision. And it is that straightforward. But in order to, when we have an unrotated entity, it's rather easy to identify corner points because that would be x, y, that's x plus with y, and so on. For that, however, we have to first compute the vectors from corner points to its center and then rotate it, and then sort of apply the reverse operation to obtain those corner points again, because they are now rotated and placed in a different position in 2D space. And again, vector math comes in handy when we start rotating vectors, because that is a corner point, that is center point, and the difference between them gives us a vector, which we can rotate by the same angle we rotate the entity, and apply, sort of add that vector back to the center, because the center doesn't move, because of the rotation happening around the center. So it's more of a like pivot point. And we can back obtain, compute those values again, which then should be mapped to the projected to the axes to be checked for overlaps. Like I said, there will be a bit more detailed version of that on this webpage, which I will include in the video description. Yeah. And also, before I forget, that page I think is that link uses, yeah, it uses Flash, but you should be able to map Flash code to Java pretty much with no effort at all because it's similar. The idea is Flash, right? So we need to obtain corner points and vectors, right? So we'll come back here to the entity class. Shall we do center? So point to the center, that gives us the center, return to the x. Actually, no, it's x plus width divided by 2 and y plus height divided by 2. This gives us the center point of our entity. Now we'll need corner points, or rather corner vectors, which is going to be a list of vectors. Corner vectors, which we can use stream for. So it's new point xy. This is the top left corner. Then we have x plus width y. This is the top right corner. Then we have x plus width y plus height. This gives us bottom right corner. And finally, bottom left is that. Those are the points. Now we need to stream and then map them. Stream, map them to. We need to obtain a vector from those points to the center, which will give us the corner vectors. Subtract center, and then collect to list. So these are the corner vectors. Vector coming from the center point to each of those corners in clockwise order. Now we will need points, or rather, corner points. So corners themselves after the rotation. Corners, that should be fine. We first compute corner vectors, then we'll need to stream them, and then we need to rotate each of those vectors by an angle, and that angle is the rotation of our entity. And we can do so again by using a nice formula from vector maths. It is the x of the existing one multiplied by cosine, which I don't have here, multiplied by cosine of the angle, which is rotation, minus p get y multiplied by sine of the rotation. That will give us the x component of the rotated vector. Now we need to obtain y component, which is similar except for the sine and cosine. So we change those. And also the sign changes. So this gives us the rotated vector. We map that vector. And finally, we need to add those, I think I missed something. New point to the we map that again. So that is already a rotated vector. I shouldn't use P, I'll use V instead. V for vectors. And that vector we now add back to the center, because center point doesn't change. And finally we collect to list. So this returns corners of an already rotated entity, which we should now be able to project to SAT. yeah, so this is where we're going to do most of the logic, or the core of the logic. We first need to obtain axes and then normalize them in order to perform dot product later. I'm going to call it axes, new array list, axes, add all, get axes for entity on rotation. So if you remember, that gives us the two axes for entity 1, and then get axes for entity 2 rotation. We also need to axes stream map. These are, you can consider them vectors as well. Normalize, going to denormalize, and collect back. Stream map collect. So our axes are now ready for use. And now for each, we also need to compute corners. Yeah, so point 2D, E1 corners, and let's do E2 corners. So these are the corner points of an after the rotation. Then we, as the theorem states, for each of the axes, we need to check if there is an overlap. And if there isn't at least on one of the axes, then there is no collision. So like I said in the previous video, it is sometimes useful to check if there is no collision first, rather than checking if there is a collision. So depending on what kind of technique of collision technique you're going to use, your approach will vary. Axes. So we need to first identify minimum and maximum value of the projection. So let's come back. So if we had, for example, this horizontal axis, then we'd have minimum projection value is that, because that is the minimum value along x-axis, and then that would be the rightmost value, or max value. Min E1 min, this is going to be minimum value for entity 1, which we can do by obtaining corner values stream, and we have to map each of the values by getting dot product between the value and the axes. So it's p now, because it's a point rather than vector, although we can treat it as a vector. And then we can use axes. We normalize them, so it should be fine now. And actually that should return a double, so we can map to double straight away. Minimum, so we don't have to count the values ourselves, we can just use one of the stream functions. Get as double. That's going to be E1 max, E2 minimum, E2 max. Stream E1 corners, E2 corners. That's min, then max, and this is max. Finally, we check if maximum value of E1 is less than E2 minimum. If that is the case, then return false, because we have found that there isn't a collision, or there isn't an overlap, and therefore there is no collision. And we can also do, in the same statement, E2 max less than E1 minimum. So in this particular case, it is kind of similar to what we did with bounding boxes, except we had two axes there, x and y, and here we're projecting everything onto a single axis, and then we check if they overlap or not. And I think that is it. Let's do a test. So there is no collision now, as you would expect, because they're far away. And if I just touch the corner of entity number 2, which is supposed to be a coin or something, then it says it correctly registers collision, which is good, because previously when we used bounding boxes, that was impossible for bounding boxes to detect. And as you can see, rotations are no longer a problem when you use a different collision detection technique. And if we were to switch back to bounding boxes, you will see the difference. So here we're colliding, but it says no collision. Here we're not colliding, but it says collision. And now if we switch it to SAT, collision happens immediately, and there is correctly no collision when we stand here. And let's just do a different angle, say 65. So there's correctly no collision, and as soon as we touch the other entity, it immediately registers it as a collision. And it works great. Well, it works as it should, and as you'd expect from SAT for a simple 2D game. In fact, you can now do a lot more with that because of the rotations. So your game can now include rotations as well. And in the future, I hope to cover other collision detection techniques as well, and a few optimization techniques. Right, so in this tutorial or video, we covered a slightly different collision detection technique, which is kind of similar to bounding boxes, but it uses projections onto axes rather than checking immediate values. And we are now able to add rotations to our entities so that you have a wider range of possibilities for your 2D games. And that'll be it for this tutorial. Thanks for watching.